The question is 241. In the textbook. Problem before we go. The question says a 50 ohm lossless line of length. So Z0 is 50 ohm. Of length L 0.375 lambda. It is given in terms of lambda. Connects at 300 megahertz. So F is 300 megahertz. Generator with the frequency is determined by the generator, by the source. And then the generator's VG is 300 volts. The phasor domain. And ZG is equal to 50. To a load ZL, determine the time domain current through the load form. Okay, so it says determine the time domain current through the load. So that would be I of L as a function of T. Or I of Z equal to 0, and I will say Y in a second, as a function of T. It says determine it for the cases of ZL equal to 50 minus J50 O ZL equal to 50 O and ZL equal to 0 or short circuit. Okay. The ones that came just now, you should pick a transmission line. The Smith job. Came in just now?
I got one. It's okay.
You got one?
Yep.
Okay. So, the question says, again, you have a transmission line and you have a source. You have a generator for everything, a source for everything, and then this generator is denoted by VG. It has a RG or ZG. In this case, it's RG2. It's like purely resistive. It's real. And then you have a transmission line. And then you have a load. ZL. We call this point Z equal to 0. The length of the transmission line is L, so this is Z equal to minus L. The Z is toward this direction. And then you have another notation based on D, in which D is equal to minus Z in the book. That's the only difference. So for the case of D, this was going to be plus L, right? Now the question says, find the current in the time domain. And you already know that we are familiar with solving all of these questions in the phasor domain. And converting it to the time domain is nothing. It's just writing the cosine and adding the omega t to it, right? So the question said, so this is at, when it says find the current at load, okay, this is I of load. Z equal to 0, or I of L in the phasor domain. When it says find it in the time domain, you just simply try to solve it for the phasor domain. Solve for phasor. Because the purpose of using the phasor is to simplify the whole math, as I mentioned. So always solve it in the phasor domain, and then bring it back to the time domain by adding the omega t. By adding cosine of omega t plus the rest. Okay? So in the phasor domain, current is equal to I0 plus E2. Since this is lossless, this is minus j beta z. If it was lossy, it was going to be omega. It was going to be gamma z. Minus gamma E2 plus j beta z. Okay. Now, last time I mentioned, so I'm looking to find this, right? This is the form. This can be written in the form of minus I0 minus, in that form as well. Now, what are the unknowns? One unknown is gamma, one of them is beta, the other one is I0, and then it looks like these are the only unknowns, right? So if we find these, we are going to be able to solve the question. So I0 is equal to V0 plus divided by Z0. And Z0 is given. So it is actually asking for V0 plus. Then beta Z, well, beta, let's say, is equal to.
Wait, I have a question. Beta Z, is that like beta subscript Z?
No, beta times Z.
Oh.
Multiplied by the distance.
I remember beta is equal to like 2 pi over lambda, right?
Right, but let's say even in this case if we need it or not. I'll show you this is not needed. But like it's 2 pi over lambda. Yeah. Then what do we have? Gamma. Unknown. Okay? Gamma I know is equal to, it's the reflection coefficient. Does anyone remember what gamma is?
ZL minus Z0 over
ZL minus Z0
over ZL plus Z1.
ZL plus
Z0.
Z0. So Z0 is given and ZL is given in part A, B, and C. So it says solve it for like these three parts. Right? So gamma, we can find it. Let's see if beta is needed or not. Because we don't have any information about the phase velocity. We do have omega because we have frequency, but we don't have any information about phase velocity. And then we can't assume it for this question. Well, let's see even if we need beta or not. So if z is equal to 0, if we equate z to 0, what are we going to find for I of 0? Because we are looking for I at the load. I of z equal to 0 is equal to I0 times e to j beta times 0. E to 0 gives what? 1. 1 minus gamma. The other one is going to be 1, similarly. Okay? So again, gamma is known here. And I0 plus is what's missing, which we have to find. Beta by itself is not needed to be known, but I will tell you that for finding V0, we will need that information. So when it comes to, we won't need that information, we will need beta times L, as I will show in a second. So in general, there's a formula in the book. Can give the number of the formula. For .82. So for V0 plus, you can use equation 2.82 in the textbook, 7th edition. And where that formula is coming from, I have not personally memorized, but I always do this. Looking from here, I always can see what? The input impedance. I have a famous formula for the input impedance from any point. And then that means I can replace that whole circuit by this. VG, ZG, Zn, right? I replace this whole thing with a Zn. Therefore, Vn is going to be equal to, based on the formula, we have V0 plus. This is where we find the V0 plus from. The purpose, because we figured where gamma is going to come from, beta is not needed by itself, at least based on that. So I will delete this, probably, or I will just add not needed. Okay? But V0 plus, we want to find that. So when you want to find V0 plus, you can either use directly this formula, or where that formula is coming from is here. Vn is equal to V0 plus E2 minus J, well in this case JBL, the length. This is the formula of V0. This is the formula of V at any given Z. You have minus J beta minus L, so that would be plus L. Questions? No? Plus gamma E2 minus J beta L. Similarly, because Vn is equal to V of Z equals to minus L. This is the famous V's formula, okay? Now, at the same time, this is equal to, this is Vn. A simple voltage division between the source impedance and the input impedance. So this is going to be Vg times Zn divided by Zn plus Zg. So this is where this formula is coming from. So because you have two formulas for Vn, or V at Z equal to minus L, and by having this as the unknown, you get this formula. Okay? Zn, this is given in the question, this is given in the question. This we found already. Beta L, I will show that this is, we don't need beta by itself. And Zn has its own formula. By replacing Zn's formula, we're able to find V0 plus based on equation 2.82. But why isn't beta L needed when it gives L something, some constant times lambda? it's gonna simplify by beta. When you multiply it by beta. So when L is equal to 0.375 lambda, therefore, beta L is going to be equal to 2 pi over lambda, which is the beta, times 3.075 lambda. Lambda is going to get simplified, and then in the answer you will have 0.75 pi. That's beta L. So you have beta L already. You have this. And then in the formula of Zn, again, you have gamma and beta L, both of which you know. Okay? So let's find V0 plus based on that formula. Well, actually, the formula isn't even simplified. So it says, this is the result, which is 2.82 equation. V0 plus is equal to this whole term divided by V0 plus is whatever that's multiplied in V0 plus. It's going to go in the denominator. So this whole term, or actually, you can do this. Let's write them separately. Vg times Zn divided by Zn plus Zg, the whole thing times 1 over that. You do e to power j beta L plus gamma to power minus j beta L. And then for Zn, we have its formula. And in its formula, we have like beta L and gamma again. It's equal to Z0 times ZL plus J Z0 tangent of beta L divided by Z0 plus J ZL tangent of beta. This formula has some symmetry which can help you memorize it, like ZL, Z0, and all of those stuff. Okay. Yep.
Could you remind me where we get the VGZN over ZN plus VG or ZG? Like where does that formula come from?
Yeah, so having the Zn here means you can take away this whole thing and then replace it with a Zn. Then you will have this circuit. That Vn, which starts right after the source or the generator, is actually the voltage of Zn.
Sure. Okay.
So based on the voltage division, you will have this times this divided by the sum.
Oh, okay. Okay.
It's just simple voltage division.
Okay. Okay.
So this is voltage division. Okay. So,
will we get a cheat sheet for the exam, or are we doing one, or are we not having that at all?
I think you will get one. So
we.
Yeah, it may even be open book. I'm not sure.
Oh my god.
Yeah,
Is it like?
I'm not sure though.
Okay.
It may not, like, you may not have a cheat sheet. You may. This is just. Yeah. So you may want to ask professor.
Yeah.
Yeah.
So the exam's in this class, right? So it's
I'm not
only
sure.
an hour?
With the-
It's during discussion, so
Discussion.
only an hour long?
Probably. If that's an hour long, then it's gonna be easy.
Okay.
Yeah, hopefully. So, okay, now in here, okay, back from the exam to here. In here, we have beta L again, which we calculated. We have ZL, we have Z0. So I'm not gonna go through the whole thing and then calculate. Just substitute them. If you have any questions, let me know.
Do you get that the last equation for Zn from the equation above of V naught?
No, this is V naught plus. Sorry. So the equation for Zn, it's proven in the book and it's a separate like equation for itself. I can refer to the number of that one too. 279. It's slightly different than this, but like that is based on the normalized values of impedances, which is actually the same. If you don't have a cheat sheet, you can definitely, I mean, you can memorize this. It has like all of those, you know, it's similar. But this one you may not be able to memorize. That's why I personally don't memorize it. Yeah. You had a question?
Equation 2.79, like isolated out of equation 2.82, or is it a different one altogether?
No, this is, so in here, again, as you have noticed, the way I solve the question, I write down the equation I need, and then whatever that's unknown, one by one I go through them. So beta L was known, right, here. Gamma was known, we already found this. ZG is given, Zn was unknown. So I try to calculate Zn separately. And then this is known, and then this we calculate. So if I have V0 plus, we figured beta is not needed. I will write it in the phasor domain, and to go back to the time domain, it's like super simple. You just add cosine of omega t. Whatever you have in the phasor domain, you have to add it over there.
Yeah, like the cumulative assumption.
Right? And then in this case, this is already found, and then we did all of that to find this, which we already found. Did you have a question?
Yeah, well, I was gonna say, couldn't we just find E from, like, since we have the frequency and like the length, can't we just find what, like, the wavelength is?
For the wavelength, you need again the phase velocity. The frequency is given, but you need the phase velocity. You don't know what the phase velocity is. The phase velocity in vacuum is like c, the speed of light, but in this case you don't know what it is. So, yeah.
Is that because we don't know what material the transmission line? Okay.
Yeah. We don't know which dielectric the transmission line is. What is the epsilon r, in other words? Yes?
20 for the homework. We have to determine what the wavelength is, but we're not giving epsilon. So would we assume that it is the epsilon for empty space, for air, or for what would the epsilon be on that one?
So in 220, I have to go through the question. I don't know the question
Yeah.
or the answer off the top of my head.
Okay.
But there's a chance that other information, if the phase velocity is given, probably you can find epsilon r. You said nothing is given?
Epsilon is not given. We only given C naught and the frequency.
It's an air transmission line, and that problem.
So would we use epsilon?
Oh, it says air. If it says air, you can just say, you can just say thank you. Yeah, 1. If it says air, you can just assume it, even though epsilon r of air is not actually 1, but it's almost, yeah.
Okay.
Yeah, if it says air or free space or, yeah. Okay. Good. Now let's talk about the Smith chart. I'm gonna delete this. Did you actually take pictures? Yes, someone?
I took it, but I will take one more time.
Also, when we use the Smith chart to find like CN or whatever else, do we need to upload the Smith chart we used for the homework, or can we just say that we found it on the Smith chart?
No, upload the Smith chart. Whatever you do, just upload the Smith chart. You don't need to explain the steps though, as long as you just move on it and show the lines and stuff. Okay. Cool. Yeah. Was I in it? Okay. That's better.
Oh wait, no. Sorry.
Okay. Again, I usually don't try to rush through solving the question because I believe the purpose of discussion is to go a little bit more in depth. Dwell on formulas and stuff, which you may not have the time to do so in like during the course, during the lectures themselves, because a lot of material has to be covered. But also, this is the type of course which you can't completely understand just by memorizing formulas or knowing the formulas or knowing which page the formula is at. If it's open book, you have to read the books like text to completely understand. So. Yes.
So for the homework, can we use Smith charts?
If it's from the Smith chart section, yeah. Because like, yeah.
And if we do, is there a degree of accuracy that's acceptable or
I think
error,
it
I
should
guess?
I think it should be fine. I mean, the numbers are not going to be off. Probably like the worst case is going to be 10% off.
Okay.
So it's going to be fine. Yeah.
Cool.
Okay. So let's see. I'll share.
Smith chart.
I'm trying to put it there in a way that I can write things on it, but quality gets lower. But you have it, so it'll be fine.
Technically.
Okay. So let's see what information the Smith chart gives and wants from us. In general, it's about gamma, the reflection coefficient. Gamma by itself is a complex number. That means it has a polar form in which you have the absolute value of gamma e to j theta r reflection theta. And at the same time, it can be written in the real plus imaginary form, which would be gamma r plus j gamma I. So similar to what I explained before, you have the real axis. So in this case, since we're plotting gamma, let's call this gamma r. And then you have the imaginary axis, gamma I. Okay? This is going to be However, the reflection logically, the amplitude, the absolute value of reflection in all of these circuits, it can't be more than 1. Why? You can't send in a wave and then receive something that's bigger. Like it just, what do you call it? I forgot the English word. It kills, violates the conservation of energy, right? English is not my first language. You already figured it. So this, the absolute value is somewhere between 0 and 1. Okay? So this whole thing is on a circle. If you remember, gamma was equal to ZL minus Z0 divided by ZL plus Z0. For certain values, for short circuit, ZL is equal to 0. This gives gamma equal to minus 1. Gamma equal to minus 1 means its real part, it doesn't have any imaginary part, its real part is equal to 1. So this point is short circuit. This is gamma equal to minus 1. Then you have open circuit. ZL equal to infinity. Infinity minus non-infinity gives infinity. Infinity plus any number gives infinity. Infinity divided by infinity gives 1. So gamma is equal to 1. It's in here. This is open circuit. This is ZL equal to infinity. This is gamma equal to 1. This is gamma equal to minus 1. And then this is ZL equals to 0. Okay? If you have matched load, matched means matched with the characteristic impedance of the transmission line. That means you have ZL equal to Z0. The denominator will be 0. So gamma is going to be equal to 0. This is matched. This is ZL equal to Z0. And this is gamma equal to 0. So the reason I'm writing these down isn't just to write something that's probably available in the book. It's because the question is not going to tell you that, okay, start from this point. The question is going to tell you we have open circuit load, we have short circuit. You have to realize, what does it mean? We have matched load, or we are looking for a matched load. We want to match the load, okay? That means we want to come to these points. Same on the transmission, same on the Smith chart. This point is open circuit. This is gamma equal to 1. ZL equal to infinity. This point is short circuit, gamma equal to minus 1, ZL equal to 0. This point, ZL equal to Z0. But we are working with normalized ZL. So normalized ZL is defined as ZL lowercase equal to ZL, whatever your impedance is, divided by or normalized by Z0. So in this case, if ZL is equal to Z0, the lowercase CL or the normalized ZL is going to be equal to 1. Okay, but these are the same. If you normalize infinity or 0, you're going to get the same thing. Now, as a general, just imagine this. Let's say I showed you this axis. First of all, don't confuse the gamma values with ZL values. This whole circle's story is around gamma, and then ZL values are within that. Okay, these small lines are the ZL values. We deal with the impedances inside the circle, around the circle, with those lines. But gamma itself is the values around the line. It may be inside the line too, because this is just supposed to be inside the circle. So, you can sense already that this is ZL0, this is ZL1, and this is infinity. So as a general case, when you are moving towards right direction, similar to all of the axes that we have dealt with, ZL increases. These are just some intuitive senses about this Smith chart. ZL increases when you go towards the right direction. But ZL has two components. It has RL plus J XL, real and imaginary components. So in this case, as you can see in your chart, these circles, okay, I'm drawing it worse than the circles themselves, but obviously these circles okay, are the RL circles. I said when you go towards the right direction, everything increases. Both the ZL increases, RL increases, and XL also increases. Both the real and imaginary part of the load impedance. So when you go from, so these are RL circles, RL value circles, okay? When you go towards the right direction, even though the circles get smaller, but the value of the RL in those circles increase. Okay? That's the general thing. Now, how about the values of XL? These circles okay, as unclear as they may seem, are the constant values of XL circles. So, with the same logic, the absolute value of XL starting from here, from these circles, going towards the right direction, the absolute value, because it may be negative too. The real part can't be negative. You don't have negative resistance. But as you go towards the right direction, the RL values increase. Okay? Now, if the question tells me you have your load equal to your Z0 characteristic impedance is 50 ohm. Your load is equal to, let's say, 50 plus 100J minus. This is not normalized yet. First, you will have to normalize it and then work with that circle. Normalizing this ZL, normalized, is going to be equal to, dividing this by this gives you 1, minus dividing this by this, 2J. You will have to find the circle that corresponds to X, corresponds to RL equal to 1, which is this circle. These are this axis, the values on this axis show the RL values. So this is 1, as you may be able to see. So this is RL equal to 1. And then minus 2j. Minus 2j comes, then 1 is here. You go forward. The values of j, these are the values of j. Okay. Minus 2j. Okay, and then their intersection is going to give you the ZL. So if I draw it like correctly, this is going to be like this, come all the way to this part, and then ZL equals to 2, I assume, is like this one, so this is going to be the intersection. So this is going to be ZL for this case. Okay, don't start wrapping up your stuff yet. A couple of minutes more. Okay? Now, you start from ZL. You will have to, in order to move on the transmission line, you will have to move around this circle. If you move in this direction, we're gonna solve more in-depth questions next week, but like, just follow through what I'm explaining so far. If you move in this direction, as it says, this is the direction towards load. Okay? The length is given in terms of lambda. It may be half lambda, it may be like 0.2 lambda. You just have to travel based on the values you see on lambda, which is the outer circle values. Let's see, I'm trying to read it. Well, these values. Okay? And then this is the direction towards generator. The opposite, well, this direction. See, I think, yeah, towards generator. So if you start from the load, you find ZL, whatever it is. Let's say the length of the transmission line, this was ZL, we found ZL. Okay? If the length of the transmission, we draw a circle like this. Just to be able to move around this line. Or actually, we can draw a line that takes this to here so that we can clearly read the numbers. Okay? Let's say if it says the length of the transmission line is L equal to 0.3, or actually, well, 0.1 lambda. Okay? And then it asks Z in. That means after traveling the distance of 0.1 lambda, what is the input impedance seen from that point? Even if it doesn't say that the length of the transmission line is L, if it says length of the transmission line is like 2 lambda, but find the impedance that you see from the distance of 0.1 lambda, you just simply move on the transmission line in the direction towards generator. So in this case, you move equal to 0.1 lambda. And I don't know how much that's gonna be, but the new point, well, I assume around here, let's say, the new point is gonna be Zn at Z equal to L. Okay. So this is the general approach to solve these questions. Please dwell on the transmission line, on the Smith chart. Try to imagine the transmission line while working with them, and then next week we'll solve more questions. Thank you. loudly, not like that. Thank you.